All set? Okay. Hi, everyone. Hopefully you can all hear me okay, both in person and people out in Zoom land. Thanks for coming today. My name is Tim Cavanaugh. I'm going to be talking about scanning electron microscopy, SEM, and some of the things that we can do with that, both with imaging and doing analysis of your materials. There we go. Great. So many of you might be familiar with SEM already. Initially, this talk was meant to be given earlier in the summer, but we moved the schedule around a bit. So typically, we talk about this prior to TEM, but if you've been attending these lectures throughout, you may have already seen the Intro to TEM lecture that Jules gave earlier in the summer. So what is SEM? SEM is a really good way for us to investigate the surface of our materials at the micro and nano scale. If you're not familiar with electron microscopy before, you may be familiar with the idea of light microscopy or optical microscopy, where light is bent through a lens and focused onto a sample to an imaging plane. With the SEM, the electron source is analogous to the light source in light microscopy. So we use a beam of focused electrons. There's one or more lenses that will focus those. And instead of magnifying the image, we want to demagnify the electron beam as much as possible to create a really fine point probe on the surface of the sample. And then, depending on the configuration of the system that we're working with, there are one or more ways that we can measure the way that that signal either bounces off the sample or interacts with the sample, so that we can learn about the sample, about its texture and topography, and maybe even what it's made of. So some of the prime benefits of working with SEM, right, are that we can exceed the resolution that we can get in optical microscopy. Best imaging resolution is down on close to the 1 nanometer scale, depending on the instrumentation and the limitations of the sample. SEM is also going to exceed light microscopy when it comes to working with rough samples or samples that have a lot of surface topography, three-dimensional texture, because we have a better focal depth than we do with light microscope. And one of the really beneficial aspects of it as well is that it's very easy as an operator to maintain this overall kind of high-level contextual view of the sample, starting at low magnification, and then also as you drive around and navigate on the sample, collect high-resolution information about those same locations, so that you're not just taking these high-resolution images in a vacuum. They're sort of tied into the overall nature of the sample surface. And again, depending on the way that the machine that you're using is configured, we can also do what's called surface analysis, so that we can learn about things like the composition and the crystallography of the sample that we're working with, as well as taking images to see what it looks like. So at CNS, I'll talk a little bit later on about some of the specific instrumentation that we do have. For this talk, I'm going to be going pretty quickly and trying to contextualize it in terms of the tools that we have, a lot of the work that we focus on. So while it's a general talk, I'll be looking at it through that lens. So kind of keep that in mind as you're watching, and maybe thinking about how that will tie into your samples and your project. And if you're interested, I can stick around a little bit afterwards, and we can talk about how it might help you. So we have 6 SEMs within the CNS universe. Again, I'll kind of go into specifics of that later. But with just hundreds of users, right? Because SEM is such a useful imaging technique and analytical technique for people from really a wide range of fields across Harvard and other universities in the area as well. So we do a lot with different types of materials, right? Thin films, 2D materials, looking to characterize the way that those types of samples might have been fabricated, or you know, how successful the structure was created, what size grains we obtained, things like that. We do a lot of work with people creating optical devices, photonic crystals, where we often have this large array of features, sometimes with three-dimensional aspects that we can try to image to characterize. We do a lot with what I've kind of called other materials here as well, which can include soft stuff like polymers, which are very challenging. So there's a picture there of zeolite materials, which are non-conductive, high-resolution imaging that's required, carbon nanotubes, and we do a lot of work with imaging different types of components of battery materials as well. So all of these fall under some material types that can be a little bit more challenging to image. We also do a lot of work with biological materials, tissue, cells. There's some broader scale things there like bird feather, right? So typically there's a lot more that will be involved in terms of sample preparation. I have some slides where we'll talk about that a bit, but it's becoming more and more common to use SEM on these types of materials as well to learn about the cellular structure or the macrostructure of some of your biomaterials. And then we kind of have an envelope of what I've called other stuff, where we get researchers maybe from some of the art museums at Harvard, the archaeological museums, geological researchers in museum, right? So such a useful tool. If you can think about it, someone has tried to put it in one of our SEMs probably. So this is an example of what one of our instruments looks like. This is our SEM14, the Gemini SEM 560. That's our highest resolution tool. So both the outside and what it looks like on the inside. When it comes to imaging, one of the most important things, right, is thinking about, what I want to see on the sample and what's the best way for me to prepare the sample, mount the sample so that I can orient that in a way that I can get the information that I need, right? So typically your sample is going to be pretty small. We have a fairly flexible chamber in that technically I think we can go up to 8 or 10-inch sample diameter, but practically speaking, most samples tend to be, maybe a couple centimeters or less. And then those are mounted in one of a number of different ways. But we do have some flexibility. Sometimes we will get those challenging samples. The one you see on the bottom here is a museum specimen, paleontological specimen. So because of its status, we weren't able to make it smaller, right? We weren't able to do anything to it. So those are some of the challenges that we have to sort out sometimes in working with larger specimens. So we're going to mount our samples, get them in the microscope, and then we have ways that we can navigate around to the different locations so that we understand what part of the sample we're looking at or which sample we're looking at any time. So electron microscopy requires electrons. In the SEM, there's two main ways that we can generate those, either with what's called a thermionic source or a field emission source. Both of them are going to be designed to get electrons off of some sort of source material. In thermionic, there's a couple of different materials that are used, but basically these are just heated up, right? And so by heating them up, we're able to stimulate the emission of electrons from the source. And then once we apply an accelerating voltage, which we'll talk about, then we get the E-beam that we use for imaging. All of the tools that we have at CNS are from the other category, which is called field emission source. And field emission source is often preferable in the sense that it's capable of higher imaging resolution. So the field emitter is also heated up. We have some reservoir of source material that's heated up and then also subjected to an electrostatic field. And those are going to make it much easier for us to get electrons off the surface in a very controlled way so that we have a more consistent electron beam where all of those electrons in the beam have a very consistent energy. And that consistency of energy resolution is going to help us get the highest resolution possible when we're imaging our samples. No matter what type of source material we have or source heating we have, we're then going to apply an accelerating voltage to turn those electrons into a beam. So the just below the tip, the filament is an anode that's held at some sort of ground potential. And then the emitter is subjected to what's called an acceleration voltage, which is the difference between the applied voltage and the ground, right? And that will stimulate the electrons that are being emitted to travel down and form our E-beam that we use for imaging. Typically, the potential acceleration voltages are from somewhere less than 1 kV up to about 30 kilovolts, which is usually the standard. It's very unlikely that you would use either of those values, right? Typically, the imaging range is somewhere in the middle of that, often about 1 kV to maybe 10 or 15 kV. But there are definitely use cases where we'll go outside of those bounds. The higher we go on the acceleration voltage, the sharper we're able to focus the beam, which is going to improve the spatial resolution. But it's also going to cost surface resolution because the beam will be penetrating deeper into the specimen. You can see there is an image of some carbon nanotubes taken at both 15 kilovolt and 500 volts. The 15 kV beam here you can see has sharper contrast, sharper peaks, so we're able to resolve, for example, the diameter of the nanotubes better. But in the low voltage, we can see that the surface texture is a lot more evident, right? So we kind of see this textural element on the surface of the individual tubes, whereas at the higher voltage, they're effectively transparent to the electron beam. So kind of balancing that out depending on which type of information is most important for a given sample and a given project can go a long way to selecting what is an appropriate acceleration voltage. So as the electrons are forming a beam, they're traveling down what's called the electron column. So we started at the top. As it progresses, we'll go through some form of aperture, which is going to restrict the diameter of the E-beam, and one or more condenser lenses, which will control the beam current, until finally at the bottom, we have what's called the electromagnetic final lens, or you might call it the objective lens, which is going to focus the beam and scan it across the surface so we can build images. So the electromagnetic lens, and again, different SEM designs will have a different number of these condenser lenses. The electromagnetic lens is a coil of wire. As the beam passes through that, when you change specific parameters, the current passing through the lens coil will change, and that will affect how much the beam is deflected as it's traveling down the column path. So we can use this to help to set, for example, how far below the lens are we focusing it? How much are we condensing the probe current to a single point, right, to affect the current density? So a lot of things are happening within the column tied to the strength of these different electromagnetic lenses. We also pass through an aperture at some point. There are typically a few different diameter apertures that we can select for the beam to go through. The larger the aperture diameter, the less we restrict the electron flow, so the higher amount of current we're going to get at the sample surface. High current is good for getting good signal to noise in our images, but it's more likely to cause imaging problems, charging, sample damage, which are things that we'll see and we'll talk about. And it also minimizes the resolution, right? So selecting the aperture and selecting the voltage are two really important parameters that we kind of want to think about each time we're starting a new imaging project. Most of the time we're doing this in an environment that's under vacuum, right? So the electron column is under high vacuum. The specimen chamber is under high vacuum. And we're doing that because in the vacuum, the electrons can travel on a straight path with fewer deviations, right? So it's much easier to focus to a sharp point and do high resolution imaging when we're working in high vacuum. On some of our tools, it is possible to work in what's called low vacuum, where we intentionally make the vacuum worse. There are reasons for that, which we'll see. We'll see some examples of when that's beneficial, but it does typically come with a loss of resolution. And so, as I mentioned, there's a few different ways that any of these systems might be configured, depending on the vendor, depending on the types of detectors that you've chosen to install for the specific purpose. And we'll see some of the good the options for that as we go through. But despite the modularity and despite the differences between the vendors, most of the main concepts are going to remain the same that we should see here. So we've talked a little bit about the resolution, right? Why we use the SEM so we can get higher resolution than with optical microscopy. And so in optics, we model the resolution as being limited by the wavelength of light, right? There are ways that we can get around that, but broadly speaking, we're doing optical microscopy up to about 200 nanometer resolution. Electron wavelength is much smaller, right? So in theory, we should be able to vastly improve the resolution over optical limits. The wavelength of an electron is roughly 1,000th of the wavelength of visible light. So you would think we could just divide our 200 nanometer limit by 1,000 and get a resolution of 0.2 nanometers, right? Unfortunately, it doesn't work that way. So there are additional considerations that we have to keep in mind when we're doing SEM specifically, that the limitation of the resolution is not purely due to the diffraction limit, but we're going to see there's a huge contribution to the resolution limitation based on the interaction of the electron beam within the specimen. As I mentioned, the higher we go on beam energy, we improve the resolution by limiting the electron wavelength, but we also penetrate into the sample to a greater depth. So those effects of depth of beam interaction within the specimen become compounded. And so we introduce this concept called the interaction volume. And so we'll come back to this in a little bit in greater depth, but we think about SEM as imaging the surface, and that's true, but it's also surface-ish, right? A lot of times our imaging signal is coming from within a few tens to hundreds of nanometers of the surface rather than purely surface imaging, which depending on the sample can make a difference. And when we start talking about some of the analytical methods that we use to characterize the sample later on, that's often even on a broader scale, maybe a micron scale. So the resolution limitation that we see isn't due to the beam itself, but due to the way that the beam and the sample interact. So if we go from thinking about a single point to creating an image, we do that by scanning the focused beam across the sample surface and moving from one point to the next. Each point is going to correspond to one pixel in the image, right? So as we move the beam across the surface, we generate a certain amount of signal at each pixel point. We do that hundreds of thousands or millions of times and put those together and we create an image, right? So the image here on the right is made from almost 800,000 individual measurement points within a single field. We can use that beneficially because that way that we form the images, that scanning method of forming the images, makes it so that as we're imaging, the beam itself is consistent. And so that makes it so that we can very easily do things like change the magnification. Because when we change the magnification in the SEM, we don't actually do anything to change the beam. We're just changing where the sampling locations are that generate the information at each pixel, right? So as we think about often starting when we look at a sample at low magnification, as we increase the magnification, we're taking the same beam, taking the same number of pixel measurement points, and just moving them closer together so that we sample the same number of pixels just in a smaller area on the sample surface, right? So that makes it very easy. If you look at this sample, this is on the right, this is a copper grid with some nanoparticles on it. Very easy for us to optimize the focus and then jump between macro scale right, at a few tens, hundreds of times magnification, up through the microscale and to the nanoscale. So we're able to kind of image these nanoparticles and also maintain their overall context as where they're located on the sample, and really tie those together.
So what's controlling the maximum field of view? Get this?
Yeah, that's a really good question. I don't think I have a slide. So it does depend a little bit on the system itself, right, and the design of the lens. But one of the most important contributors to what controls the maximum field of view is what's called the working distance, which is how far our sample is away from the lens, right? So if we kind of go back to this image here where you're seeing the scanning, right, we have some limited limited amount that we can scan the beam back and forth, right, which would be this angle.
Oh, sure, yeah.
And so if your sample's farther away, right, that's going to be a greater maximum field of view than if you do it closer to the lens. Cool. Often that maximum field of view will be on the order of, I would say, between 1 and 5 millimeters, something like that. So that kind of leads here where sometimes the maximum field of view isn't enough, right? So sometimes we want to characterize a sample that's centimeter scale or even greater than that, right? And we do have on some of our equipment the capability to do this in an automated way by taking multiple images at high or medium magnification and automate the collection and stitching of those into these large mosaic scans here, right? So each of these examples is made from about 100 different images that have been automated and stitched together into the kind of macro image here. So I think that, if I remember, that's some sort of fossilized mouse tooth at the top, and on the right is fossil insect burrow, right? So these are, biological, paleontological applications, kind of 10 millimeter plus sample size, right? So we can't really characterize that without doing this stitching procedure. So when you kind of think more about magnification, right, it's a tough concept because it doesn't always tell us all the information that we need, right? So the magnification is going to be based on the width of the image field of view, both on the sample and how it's displayed, right? But these are two different images taken at the same field of view, same magnification, right? These are both at 5,000 times magnification. But on the bottom, we've controlled it so that we have almost 10 times as many pixels creating the image, right? So it took us a lot longer to collect this, but I have so much more information as we zoom in on these gold nanoparticles because the magnification has stayed the same, but the resolution of each pixel is so much better, right? About 3 times better, that I'm able to gain a lot more resolution, a lot more information about this sample by doing that. Conversely, right, here's another image of some gold nanoparticles. On the left, I've kind of showed inset where I blew up on the right. And the image on the left is already taken at 500,000 times magnification. So the full field of view is about 600 nanometers. We went ahead and increased the magnification to the maximum, but I don't think we actually gained any more information, right? Because we've kind of crossed this threshold where the microscope will let us keep magnifying, keep zooming in, but we're sort of past the practical limitation of now each pixel isn't really reflecting a true increase in the resolution of the system. So we haven't really learned anything by zooming in more on that. So magnification is a parameter that people want to know, and you want to kind of keep that in mind as you're taking images and sort of navigating around your specimen. But often I think it's more helpful to think about what is the field of view of the image, what is the size of each pixel, because those can sometimes be a little more helpful when you're thinking about the data that you're seeing. Okay, so going back to thinking about this idea of the interaction volume, we have different signals and where they might be coming from. Starting with imaging, we have two main types of imaging signal. We'll talk about those, and then I'll transition over and talk a bit about some of our analytical methods. Imaging breaks down into two main categories, which are secondary and backscattered electrons. Both of them come from different places and tell us different information about the sample. Secondary electrons are from the sample. They are knocked out by the beam, and they often carry information about the surface topography or roughness. Backscattered electrons are coming from the primary beam that enter the sample, undergo some elastic scattering, and may come back out, in which case we can detect them. And the likelihood of that happening is based on the atomic number of the material. So the backscattered electron signal carries compositional information. Back to that. So the main way that we can differentiate between these two is through the use of an energy filter of one sort or another. Because BSEs tend to be, because they're coming from the primary beam, they tend to be higher energy, right? So they have an energy that's very close to whatever the acceleration voltage is that you chose. They're on the high energy spectrum of the electron signal. Secondary electrons are starting basically at rest within the specimen. They're just sort of loosely held, so it doesn't take a lot of beam energy to knock them out. So they tend to cluster below about 50 or 100 electron volts. So we can really see we have two distinct populations of electrons, one high energy, one low energy. With BSE, we see that also their energy and intensity, frequency will correspond, as I mentioned, to the atomic number of the material, right? So we're using BSE imaging to try to learn about the different phases that are present in the sample. There are, go ahead and then come back. Bear with me. Okay, secondary electrons are coming from the sample. As I mentioned, they're not dependent on the atomic number of the specimen, but instead are going to reflect variations in the sample surface topography, right? So coming back to the idea of the interaction volume, we saw that there's a limitation on the resolution of the imaging based on how the beam is interacting within the specimen. And that's going to be based on two main factors. One is your acceleration voltage. So higher voltage, you can see, is going to cause much greater depth of penetration, much greater signal depth. And just kind of modeling that out, if we do this simulation on silicon, as we ramp up the beam from 0 kV to the kind of the maximum 30 kV, you can see we have this very exponential growth of how deep our beam is getting into the sample and the trajectories of the electrons within the specimen surface. And again, another example, seeing that on the imaging, what that means on the imaging, looking at these carbon wires, right, at low voltage on the left, we have not as much sharpness, not as much resolution, but much greater sensitivity to the surface. So we can kind of see where these are maybe having some surface texture, how they're kind of stacked or layered in 3 dimensions a little bit better. On the right, at the higher voltage of 20 kV, they're basically transparent to the beam, right? So the beam is going directly through these thin samples. So we have very good sharpness, very good edge definition, but it can become a little bit complicated because you know, we're basically seeing through them in a way that we lose a lot of information about the sample texture. So again, surface-specific information, looking at these, this is a gold nanoparticle sample, we see kind of highlighted there's some surface contamination that's readily visible at low voltage. So maybe some just hydrocarbon contamination or something like that. However, at high energy, that thin contamination layer is just making up such a small part of the electron signal that we don't even really see that in the image. The other half of the interaction volume equation is what's the material that we're working with, right? So we saw that depth increases with voltage. Depth also decreases with increasing atomic number, right? So higher atomic number elements have larger nucleus and more what's like stopping power. So because they're bigger and heavier, they're basically stopping the beam from penetrating as deep. So this is modeled at a 5 kilovolt beam. You see going from silicon to iron to gold. As we kind of increase on the periodic table, we're going to shorter and shorter depth within the specimen. So a lot of these effects become amplified with a lot of the more challenging, lighter element materials that we might be working with, where the penetration depth becomes a really significant issue. And as you can imagine, most people aren't working on pure materials, right? So you might have a layered material or a multi-phase material where it's not as straightforward. We're not able to model that quite as easily if you do have different phases or different materials that are present in your sample, because they're going to interact differently to the same beam, right? So always, you always want to kind of keep this in mind in the context of what your sample is, what your material is, and the type of information that you're trying to learn. All right, so when it comes to detecting BSEs, there are a couple of different ways that we can do this. I'm going to kind of go through this quickly, and here I'm going to focus on the first type, which is called the chamber backscatter detector. This is a fairly old style detection design where it has a silicon diode on the bottom of the detector, which may be segmented or may not be segmented. The beam will go through the middle of the detector, generate the BSE signal, and then we'll measure the backscattered electron signal underneath. So if you remember back, the backscattered electrons tend to have higher energy, right, than secondary electrons. This type of detector requires a certain amount of energy basically to generate these and any sort of capacitance on it, right? So any sort of signal. So it's fairly immune to secondary electrons and is only going to register backscattered electrons. It's fairly slow. As I mentioned, it's kind of an old style design, but it works very well by sitting directly above the sample to give good signal to noise, and really helps discriminate between different phases or different materials that you do have present in your sample. It may be segmented, which can give the user some control over exactly what type of BSE signal they want to collect. We can get into that a little bit later. But it's, yeah, so it's also fairly slow processing. So looking at this sample, this is a polished rock sample. We see we have a few different mineral phases here that are showing up in various different grayscale. And you can't really scan too fast with the BSE because the image on the left, as you can see, is just really poor quality. On the right, as we slow it down and do a longer exposure time, we're able to get a much nicer high resolution image. Most of the time, though, most of our users at CNS are more interested in secondary electrons. And so secondaries come in a couple of different detection methods as well. I'll talk about both of these. Basically, they're going to break down into where the secondary electron detector is located. So there's an in-chamber style, which is called Everhard Thornley. Here it's labeled as SE2. That's what we call it on our Zeiss SEMs. And they are located in the chamber. You can see here an example of one of our instruments. That's the detector circled. You can see it kind of sits off to the side. It has a biased Faraday cage on the end to help to attract as much signal as possible. And because it's sort of sitting on one side, you get these differences in illumination and shadowing, and you get these images that give a very three-dimensional appearance, right? So here's some kind of bug, and it's got all these gross little hairs coming out of it, and you see those looking nice and 3D, and almost like looking at a black and white photo. There's another type of SE detector, which is called in-lens. As you might guess from the name, it's located above the sample inside the objective lens. And so that means it's sitting sort of looking top down. So you lose some of that topography and shadowing that comes from being located in the chamber. So the images are a little more two-dimensional, but but the position of the detector inside the electrostatic field of the lens sort of works as a built-in energy filter so that it's more sensitive to very low energy signal, which tends to have more positional resolution so that it's coming from as close to where the probe hit the sample as possible, right? So in lens is going to give us the best possible spatial resolution. And so you can kind of see that here. This is an example of some kind of marine algae, I think, that forms these silica plates on its surface. And SE2 on the left, you kind of get that, 3D aspect. You can see this thing kind of looks like a ball. It's got some shadows. It's got some roughness. On the right, we get a little bit better sharpness on some of the more fine details, but the overall image appearance is a little more flat. The nice part is that it's very easy to take both of these either in sequence or even simultaneously, so we can get this information using both detectors without too much difficulty.
So what's the material?
This is, I forget the name of it, I'm sorry. It's some sort of marine planktonic organism that lives in the ocean and creates this exoskeleton. Yeah, basically, exactly. Yep, exactly.
Let's work.
Yeah, exactly. Well, yeah, so we can very easily kind of toggle between different detectors or even look at them at the same time, so we can get this complementary information stream about the sample. Okay, based on time, I'm going to skip through some of this because I have too many slides and not enough time. Yeah, definitely. And I want to spend a few minutes talking about the analysis potential as well, right? So we can do high resolution imaging, we can do secondary and backscatter imaging to learn about the composition or the roughness of the sample. But a lot of what we do is also doing what's called analytical work, where we can try to determine the composition of the sample or some of its crystallographic properties. So starting with what I've called here electron beam microanalysis, that's going to encompass both EDS and WDS, which are different ways that we can measure the elemental composition of the sample. EDS, some of you might be familiar with, is called standing for energy dispersive spectroscopy. So we saw some model before for how the beam might create a secondary electron or a backscattered electron. There's another thing that can happen as well, which is that the beam can create a secondary electron from the inner shell of a sample atom rather than the outer shell. That will create a vacancy in the inner shell. The atom doesn't like that, so an outer shell electron jumps down to take its place, and during that transition event, the sample atom gives off an X-ray. EDS works by capturing those X-rays, measuring their energy level, measuring their intensity, and we can translate that into elemental information about the sample and about the point where the beam hit the specimen. There's a couple of different things that we can do. We'll see some of the different types of data that we can generate, but we can also think about this both in qualitative terms and quantitative terms. Qualitatively, right, we can use EDS to figure out, okay, what elements do I have? Where might they be localized on the surface? How are they interacting with each other? So that, sort of what sort of different phases do I have, not just what elements are present. We can take that another step further and turn that elemental data into a quantitative result, so I can figure out not just what elements are present, but what concentration are they in, and maybe what compounds do I have. So when we produce X-rays by hitting the sample with the electron beam, they will be characteristic to the element and to the specific vacancy that was created. So these are called characteristic X-rays because they have a known energy, and if we can measure the energy and the intensity, then we can sort of work backwards to figure out what element we have present in our specimen. So in order to do this, we often look at this kind of special periodic table where in addition to having the elements and the atomic number and the atomic mass, if you look at the bottom, you can see we also have characteristic X-ray energy peaks that are expected for each element, right? So for iron, based on characterization, we expect that if there's iron in our sample, it will have X-ray peaks that we can measure at 6.4 kilovolts and 0.7 kilovolts, right? That's helpful information to have because in order to actually make any of those X-rays happen, right, in order to generate the signal that we need to get this information about our sample, our electron beam needs to have enough energy to actually produce those ionization events. So the critical ionization energy is usually taken to be about double for any specific X-ray line that we're hoping to measure, right? So for iron, if I want to measure this top line here at 6.4 kV, I'd want to have, a minimum acceleration voltage of 12 or 13 kilovolts, something like that. So at the beginning, I mentioned that our acceleration voltage range goes up to 30 kV. So a lot of times when we're using these higher acceleration voltages, that's when we're doing the EDS analysis, depending on the materials and the elements that we expect to have present in our specimen. So we expect these peaks at 6.4 and 0.7. And fortunately, when we look at an iron spectrum, we see a peak at 6.4 and 0.7, right? So it's nice when things match what you expect them to. If you take a look, there's actually more peaks though, right? So there's the iron peak at 6.4, and then there's another little iron peak here next to it, a little bit higher energy, and that doesn't show up on the table, right? So depending on the element that you're looking at and sort of the specifics of its orbital configuration, we may have one or two or many, many X-ray lines that we can work with. Those are named in such a way that we know both where the electron vacancy was created and which electron was able to replace it, right? So if you may have seen KLM shell notation before, right? We're going to refer to the different X-ray lines as something like K alpha, K beta, depending on which orbital the vacancy was created in. For K alpha, it would be created in this innermost shell and where the replacing electron came from. But the K alpha peak here is the one that we see at 6.4. The K beta is this little one next to it, right? So typically the major notation is going to be for the alpha line in each group. So the basic information that we get is going to come in the form of a spectrum. Here, this is a spectrum of gold and silver alloy, and it's basically a histogram plotting the intensity of the X-rays and their energy level. So we can see where we have peaks, where we have large concentrations of specific elements. And then we also get what's called the background curve, right? So we don't just see peaks here. We have a pretty strong background curve that's going to be present in the specimen. And the background curve is going to be present in every sample, and it's caused not by characteristic X-ray emission, but it's created when the beam is interacting with the sample in such a way that it loses some energy but does not produce an ionization, right? So often we get this kind of gentle sloping background curve that we see, and that should go up to 0 at whatever our acceleration voltage is that we chose. When we think about the spectrum and some of the ways that we can use that as data to understand our sample, there's two different ways that we can collect spectra, really. One is sort of a bulk analysis where we can integrate over a large field of view. That's great if you have a bulk material and you want to sort of characterize it broadly. We can also do point or area spectrum, where if you do have more than one phase, you don't want to kind of conflate all the different elements from multiple phases into a single spectrum, so we can actually localize where the spectrum data come from. When we're doing point spectra, we really want to be sort of hyper aware of what we can model the interaction volume, right? Typically, we're working at higher voltages for doing EDS, so the interaction volume is larger, and we don't want to do a point spectrum on a feature that's smaller than our interaction volume, because that's then going to be still giving us signal from some of the surrounding phases or matrix. And then we can also do X-ray mapping. So X-ray mapping is a way that we can collect spectrum data across an area and turn that into an image, right? So by collecting information at every single pixel within an imaging field, we can make an intensity map for a given element peak at every pixel and turn that into map data, right? So we can then do that for multiple element channels and really get a visual understanding of the distribution of where the different elements are located. This is a silicate particle coated with carbon on a silicon wafer slide, right? So we can see not only where we have the different elements, but also what their relative intensity is and what the distribution is of the different elements, and how those kind of combine, forming the overall sample elemental distribution.
Tips for this random, if not to XPS.
Yeah, so we usually, mental model is usually about 1 micron, right? So not as surface sensitive as XPS, but it will depend a little bit on the sample and some of the settings. We can also kind of go one step farther with element mapping, and under certain circumstances, we can get quantitative data out of X-ray mapping. So these are 2 maps of the same area. On the left, we see it's what's called a qualitative X-ray map, where the brightness is showing the distribution of iron in a few different mineral grains. So you can kind of say, where it's very bright, I have more iron than where it's sort of medium, and more than where it's dark, right? However, by doing this fully quantified, we can actually convert those into numerical values, right? So I can say, okay, in the center, I have, somewhere around 40% iron by weight, whereas in some of these less intense areas, it might be more like 20%, right? And so that can go a long way when you generate these for each individual element, to kind of understanding not just where the elements are distributed, but sort of what phases they're forming when they come together, right? So this is really useful for kind of characterizing multi-phase materials, especially. Cool. So EDS is really great. EDS can tell us lots of information about the sample, what elements it has, where they're located. Sometimes we can be quantitative with it. However, for certain samples and certain analytical projects, EDS is not sensitive enough, or it doesn't have good enough resolution. And when EDS is not good enough, we have another tool at our availability, which is called WDS. So EDS was energy dispersive spectroscopy. WDS is wavelength dispersive spectroscopy. So it is measuring the exact same signal as EDS. We're measuring characteristic X-rays. But rather than measuring the entire spectrum at one time, the X-ray signal is first going to pass through a crystal spectrometer, so that we are only investigating one single wavelength at a time. So this is an example EDS spectrum where you can see, this is from a mineral called monazite, which is a phosphate that has a number of different rare earth elements in it. Those are arranged in such a way that they overlap with each other terribly, and we can't really reliably resolve which of these elements is present and which are just being caused by overlaps. So there's not enough spectral resolution from the EDS to get the full picture of what we want to see here.
Explain more WDS.
Yeah, so hopefully, as we see a couple of the next slides, it'll become a little more obvious what the difference is. So this is kind of an example of the WDS detector. The X-ray signal will go in, interact with one of the diffracting crystals, and it will only reach the counter, the detector, if it is the specific wavelength that is currently optimized for on the crystal. So it's actually a really cool setup, because the WDS spectrometer contains multiple diffracting crystals, each of which is useful for a specific portion of the X-ray spectrum. So it's able to diffract a certain wavelength range. And if you're familiar with Bragg's law, and I guess even if you're not, we're able to manipulate the position, the selection of the crystal. And you can kind of see, hopefully from this animation, that the crystal itself can actually rotate in such a way that for a selected wavelength at any one time, Bragg's law is satisfied so that the signal will come from the sample off the crystal and make it to the detector. Okay. So we're able to satisfy Bragg's law by controlling both the D spacing, the crystal spacing parameter by choosing the crystal that we have, and controlling the theta angle by adjusting the rotational position of the diffracting crystal. Fortunately, this is all automated, right? We don't have to do any intense calculations. This is controlled for by the software once we determine which wavelength we're trying to measure specifically. It does bring up some choices sometimes where one, if you look at the energy range for the different crystals, they do overlap with one another, right? And so it's possible to measure the same signal with one or more different crystal. So kind of taking a look here at this spectrum from a steel sample contains titanium, and unfortunately, the titanium alpha and beta peaks here, one is on one side of the crystal threshold that's been selected, and one is on the other. So we have this really sharp edge here where we're switching from one crystal to the next. So we just want to be thoughtful about selecting the right crystal for the right element that we're trying to characterize. And you can see that the background of the EDS, which we see in the yellow, is this kind of sloping, gently curving, typical Bremsstrahlung shape. The background for the WDS is based on the shape of the crystal intensity. And unfortunately, that's kind of non-linear across the diffracting range of the crystal. So we do get these really sharp edges. And from one side of the crystal to the other, we're going to get different performance characteristics. One might give you better signal to noise. One might give you better resolution. So we're just having to be thoughtful about selecting the right one to answer the question that we have.
So
That's okay.
the energy range is so wide, like 0.7 to 0.8 is same to D. It's really hard sometimes to determine, right?
Yeah, and so we actually don't have all of these crystals available. I think we have 5 or 6 different crystals on our spectrometer. Right, so we just want to make sure that we can cover the full range of the X-ray spectrum without, any gaps, so that we can measure all elements that are present.
Actually, I don't like it what the gain is of having this diffraction filter versus energy recall factor. Like, why is it make anything sharper versus want to get this energy?
Sure. So hopefully this will show you a little bit. Looking again, this is a steel sample, I believe. And here we've got the WDS in that kind of purplish overlaid on the EDS spectrum of the same sample, same point, right? And so the WDS peaks are up to 10 times narrower. So we have that intensely focused spectral resolution that's caused by not diffracting any X-rays to the counter, to the detector, that are not at the specific defined energy channel, if that makes sense. So the EDS peaks that you see are sort of a histogram of the best guess of the EDS detector at assigning the energy, right, at any one time. And so the true EDS value, right, is at the peak center. It's just the limitation of the EDS detector design that it can't accurately assign the energy of every single X-ray within that region.
So if the EDS detector was like ideally perfect, it would just give you the same plot. It's just that it's not seeing this extra thing that does filtering.
Sure.
That makes sense.
And you don't need it all the time, right? And in many cases, honestly, most cases, EDS, if you do a good job of it, is more than sufficient. But WDS is something that we can do when it's not good enough,
That makes
right?
sense.
So I've kind of blown up a little area here where it looks like from the EDS, we have, one peak for chromium. But on the WDS, because we have such narrower peaks, we're able to see that there's actually a small manganese peak hiding there in there as well.
So for your like alloy,
Mhm.
if we do nanoparticle, like a nanomaterial, nanometal to like doping some of alloy to make the property change. So how about the sensitivity for this technology WD?
So sensitivity is very good, right? Yep. So we have better peak resolution, and we also have much better sensitivity. If you kind of characterize here the peak to background, because the background in the WDS is much smaller. So often we can do, you can kind of see that here, right? We can get down to tens, hundreds of ppm measurement sensitivity in WDS. EDS, we're usually at, about halfway percent. The sensitivity is much better. Problem is, nanoparticle is not a word I like to hear with WDS, right? Because often we're kind of modeling that our signal depth is micron scale, right? Hundreds of nanometers, yeah.
Nanomaterial, you have a lower melting point, which make it better.
Yeah. Yeah. So if you're trying to do a bulk characterization, that sounds good. But if we're trying to do, nanoparticle analysis, WDS is not often the best choice.
I see. Now, into the alloy is you make the melting
Got it.
point. The temperature is lower.
Okay.
So you can form better alloys in the nanoscale
Sounds good.
sensitivity.
Okay.
Thank you.
So better resolution and better sensitivity. Yeah.
You had crystals that were for like beryllium and light elements.
Yeah.
I remember hearing just like EDX isn't super good for things. So is WDS okay with these elements, or is it just like
Neither one of them is super good at light elements. EDS should be probably a little easier. Where back do I want to go? Often the problem with EDS and light elements is, I'd say it's kind of twofold. You often have more overlaps with light elements because there's more X-ray lines in that part of the spectrum. And also, if you kind of look, that's where the background curve tends to peak, right? But if you look at this spectrum, we're more than capable of doing a good quantification on carbon, oxygen, nitrogen, things like that. So I usually try to do light elements by EDS when possible, but either method can technically go down to beryllium. Well, so why don't we do WDS every time if it's so great and has great sensitivity and good resolution? Takes a lot longer, right? Since instead of collecting the whole spectrum in one go, we're having to look at every single wavelength individually. There's a lot more setup involved. EDS, very easy to just kind of do what you might call point and shoot, right? Whereas WDS, we have to do standardization and kind of this careful setup of the individual analysis points. And it's just not as common to find WDS spectrometers in the lab. We have one system with WDS capability. I think we have, 4 or 5 SEMs that have EDS capability. So it's just not quite as common. Cool, new thing coming. This is a detector which you may have seen if you've been in the lab at all in the past couple weeks. but it's sort of a new design, which is basically a hybrid backscattered electron and EDS detector. We currently have a demo unit installed, but we will be putting a new unit on one of our Gemini SEMs at some point in the fall. It is similar to the type of BSE detector that I showed you in that it comes in and sits right above the sample. And because of that, it has much higher collection sensitivity and can do EDS about 20 times faster than a conventional EDS detector. So you are basically doing EDS mapping, element mapping at imaging speed. So it's pretty cool. If you're interested, come talk to me. Great. I know we are definitely over time, so I'm going to quickly go through another type of analytical capability we have, EBSD, electron backscatter diffraction, which can tell us information about the crystallography of the sample and the orientation of the different crystal grains that might be present in your specimen. So this works by taking your crystalline specimen, putting it at a very high tilt angle, and basically taking a snapshot of the projection of the cone of diffracted electrons that are coming out of the surface. And if your sample has a crystal lattice, those electrons will come out preferentially along the lattice planes as sort of a predefined escape route, if you will. So we can model that based on a specific phase geometry, specific lattice parameters. Those diffracted electrons will come out in predictable ways. This is a simulation of different spherical diffraction patterns from a cubic steel lattice. And we then take a photo of those as they hit a detection screen and form a 2D projection of that spherical simulation. The software that we use will then do what's called indexing, which matches the snapped photograph that we take and figure out what is the orientation of the lattice parameters of the material at that point where you generated that information. Pretty cool. Where this becomes useful is that we can then do this across a large field of view, right? And so if we have more than one type of phase or multiple grains with different orientation, we can actually do what's called orientation mapping and see how the grain structure of your crystalline sample changes across the surface. Some of the types of information we can get out of that are grain size. So on the right there, we can map the individual grains in the steel sample and figure out what the grain size distribution is. We can figure out if there are different phases present, right? So this one is showing a ferritic steel sample with some austenite inclusion, so we can kind of learn about what the temperature history of that sample might be. And we can also have the sensitivity to map some sort of localized intragranular deformation. So this is a sample of a meteorite, and we've mapped some of the internal weaknesses within some of these grains, which helps us to reconstruct its history from the EBSD information. Cool. So we can do a lot with SEM. We can get high resolution images. We can get good analytical information to learn a lot about the specimen. And we can do this on a really wide range and wide variety of samples. We have quite a few SEMs within the CNS universe. Here's just some information about some of the ones we have. I can leave this up if you all want to look at it, but we have 6 SEMs available. One of them, the SCC SEM12, is just down the hall, and the other 5 are located in Cambridge. But definitely reach out to me if any of this sounds like it could be useful for the type of work that you're doing, or if you'd like to learn more or discuss any projects. Thanks.
To reach out to you for the crystal boundary orientation.
Definitely. Sounds good. Yeah, feel free to reach out and we can discuss kind of the specifics of what would be involved.
I know that the scanning has to occur like a high vacuum, so I was wondering how biological samples are prepared because you have like water in the cells. How do you sort of
Yeah,
and sort of keep the integrity of the sample?
great question. I skipped through a lot of that, right? So a lot of samples don't play well with high vacuum or high energy beams. So we do have the capability to do imaging on biological specimens. Just takes a lot more work getting there, right? So most of the battle on that is on the sample preparation side. So for something hydrated, we're typically going to do a critical point drying or cryo-SEM. Okay, so those are kind of the two main branches I would suggest. I don't really deal with cryo at all. Adam, who works here at the SEC on this instrument, which has the cryo-SEM capability, will be the person to ask about that. But for CPD, that's basically going to take those hydrated samples and we replace the water in a really controlled way. So first, after the sample is fixed, it will go through an ethanol series to kind of gradually drive the water out and replace it with ethanol. It then goes into the critical point dryer, which will replace the ethanol with first with liquid CO2. That's then heated up past the critical point of CO2. And then it is removed. The pressure and temperature are returned to ambient conditions, and the liquid CO2 has been replaced with gas phase. So there's now no liquid left. We've done it in a controlled way so that there's minimal structural deformation of the sample, and then it's safe to put it in high vacuum and you don't have to worry about dehydration. Any other questions?
This is a bit like me specific, but
Yeah.
in general, with the issue of surface roughness,
Yes.
I'm trying to do like an EDS map of oxygen concentration over surface. And of course, I noticed that like the topography of the sample is very like,
It's going to have a huge impact. Yeah.
yeah, which is not so much of a case with the heavier elements. Nice. So is there any way to account for this, or is it just like I have to polish it, or it's just not viable to?
What is the sample?
It's a rare earth like nickel oxide.
Cool. Yeah, so some facilities will deal with this by having multiple spectrometers, right? Once, from different angles so that you're capturing that from different angles and minimizing the shadowing that way. We don't really have any system set up like that. Yeah, so it makes sense that you will have more trouble with the light elements because they're more surface, that signal is more surface sensitive. That topography is going to be highlighted. That's a tough one. I was going to suggest that our new fancy detector that I mentioned would be helpful because it sits above the sample, right?
Oh yeah.
And so the solid angle is much better and you're not dealing with any of that angular specificity of being, only on one side. Downside to that is that this detector has an energy filter, so it's not sensitive below sodium. So if you're imaging anything, or if you're mapping anything below sodium, it's going to revert to using conventional EDS for that anyway. So yeah, no, I don't have a great answer for you other than, minimizing the topography as much as I can.
And polishing, I know it's the whole thing, but would you like recommend using like a fib to polish if my sample is kind of fragile and I can't really like sandpaper it well, or some other?
Yeah, I mean, it depends on the scale that you're trying to characterize at. You can use a fib or an ion polish, or you could try, if you know the orientation of the system, you could also try tilting the sample, right? So if you're tilting the sample towards the detector, that might take away some of the topographic issues as well. But yeah, you could try fib.
Did anybody try this instrumentation? for the like a battery material, when you charge, discharge, you have a crystallization, maybe change it gently and gradually for the dynamic study. And another is a solar cell.
Mhm.
If light illumination, some of the
Yep.
other reaction some way. So you have photon, electron recombination, but some of them got a charge always there. So you always decrease the efficiency.
Yeah, so like some in situ experimentation.
Yeah.
We do have that capability, right?
This is the light. Anybody did this type of dynamic study?
Not, I have not worked with any dynamic in situ experiments on like solar cells, but in theory, we have the capability to set up some in situ experimentation, like applying voltages and things like that.
After PhD, you work on that.
Could be interesting. Yeah, if that's something that you think would be useful, we can talk about what would be involved. Yeah. Yep.
The battery, like a lifetime, this
Right.
why the efficiency sometimes decrease.
Yeah, and kind of seeing how that changes
Like change new material.
after usage. Yeah, that would be interesting.
Thank you. What's the master? PhD.
All
Which
right.
SEM does this one live on now, or the demo?
It's still a little bit up in the air, but it's probably going to be Gemini 360.
Okay, makes sense.
All right.